remembered it now.
Yeah, it's better than not at all.
Okay, hang up for a minute. I will. Reliability. Let's just back up one. I'll give you like the crib sheet version here. Okay, so going back a second. Okay, here's our reliability, right? So we got our reliability, and notice the sub J. So we get a reliability of the estimate of the true school mean for every school is a function of how not the between cluster variance. How much variability is there between clusters, right? The more variability there is between clusters, the better able I should be to see, right? The better able I should be able to estimate this thing. And then the amount of variance within cluster, and this one I think is really easy to see. Like if there's a ton of within cluster variability, that means, again, think about math achievement. If I've got something like math achievement and within a school, people are varying from like, often think about something like math achievement. You get like 3 standard deviations worth of difference within a school, either way within a school on math achievement, right? You got some kids who are like really, really low and other kids who are really, really high, and you get kids in the middle, but you get this huge spread on math achievement within a school. So that's like the within cluster variability, right? Well, assume we group mean centered it. So now I can think about it as the within cluster variability. So if there's tons of variability within clusters, right, then I need a bigger sample of people within the cluster. I need a bigger N sub J, because imagine I've got like basically 6 standard deviations of difference between the highest and lowest people in the school. Again, bell-shaped curve, so it's not uniformly distributed. If I only take 3 people from the school and I compute a cluster mean on those 3 people, I could be way off what the real mean is, right? But if I take 100 people from the school and compute the school mean, I should be a lot closer to what the real school mean is, right? And if I take 1,000 people from the school and I compute the cluster mean, I should be closer still, right? And so we talk about this sigma squared over N sub J is this error variance. It's the variance in the error of estimation. And it's driven by how much variability is there within a cluster, and then sort of holding that constant, how big is the cluster size? And so tau naught and sigma squared, those are estimated for a given model, and we have one tau naught and one sigma squared for the whole sample, but N sub J differs across the different clusters. And so what I was starting to say is, like, imagine you've got a cluster with 5 people and another cluster with 500 people. The cluster with 5 people, the reliability is going to be tau naught over tau naught plus sigma squared divided by 5. So maybe the reliability is like 0.3 for that cluster. Whereas in the cluster with 500 people, you've got tau naught over tau naught plus sigma squared divided by 500. So now that term is going to be way smaller than it was when it was divided by 5, right? And so now maybe the reliability for that cluster mean is, I'm making these up, right, because we don't have numbers, but let's say for the cluster mean of 500, the reliability with which I can estimate the true mean is like 0.95. Whereas when I only have 5 people per cluster, the reliability with which I can take the mean of those 5 people to estimate the true cluster mean might only be 0.4, right? Yeah. Well, it's going to range from 0 to 1, right? So technically it's going to range from the ICC to 1, but if there were no interclass correlation coefficient, so if there were no between cluster variability, then it's going to range from 0 to 1. So 0 would mean basically there's no between cluster variability, right? So anyway, heuristically, higher is better. And in my experience, this isn't like Chromebox Alpha where you're going to do this and be like, my average reliability is less than 0.8. I'm not going to use my model. No, because in fact, I'm going to show you what ends up happening when the reliabilities are lower. But generally speaking, in an unconditional model, you'll usually find that the reliabilities for the intercepts, the average one is high. Usually in my experience, 0.9 is not uncommon, on average. But if you dig in and you actually get the reliabilities for each cluster, you might find that lots of clusters have really high reliabilities, and there might be a couple clusters that have really low reliabilities. Why are those clusters going to have really low reliabilities? Smaller sample size, right? Because we're using the same sigma squared and tau naught naught. So the only possibility for why a cluster is having a way smaller reliability is because they have a really small cluster size, right? So if you find, I will give you a rule of thumb, if you find that the reliability is close to zero, let's say like less than 0.1 or less than 0.05, I've seen both of those sort of floated around. If the reliability on average, not any one cluster, but if on average the reliability is less than, let's say, 0.1, that might be a signal to you that you don't need that randomly varying coefficient, that you can't really, right? You can't really make these distinctions in terms of the intercepts or the slopes across schools. So you don't really need that randomly varying coefficient. But in general, we're not, unlike alpha, we're not like, oh, it's got to be above 0.8 or we're sunk. We're just this. And a lot of people don't even look at the reliabilities, though they probably should. But so higher is better. Less than 0.1, I would say, is problematic. And probably indicative that you're trying to estimate something as randomly varying that you don't need to. Okay, so talked about that. So again, just to kind of reemphasize this, there are these two competing estimates you could imagine for the true school mean. The overall, again, imagine we've got an unconditional model here. So we've got gamma naught naught, right? That's our overall mean. And so you could say, like, if I don't know anything about this school's mean, what's your best? So imagine I had 0 people in a school, okay? So I have 0 people in the school. So I have no information. I can't even compute a mean for this cluster. And I ask you, what's your best estimate of the mean for that school? What are you going to say? Yeah, well, yeah, again, we're in an unconditional model. You're right about the similar school thing. But for now, let's just say I don't have any predictors at all. So all I have is gamma naught naught, which is basically an estimate of the overall mean, right? If I know nothing about this school, what's my best guess about the school mean? The overall mean, right? Because I have like no information about this school. So my best guess would be the overall mean in the absence of any information, right? So that's one sort of competing estimate for a true school mean would be like the overall mean or the expected value across the entire sample. Like right now, just for simplicity, we're thinking about an unconditional model, but this would be true even if you did have a bunch of covariates. It would be exactly what Luis was saying. In that case, it wouldn't be the overall mean, it would be the model predicted score for that school based on the set of covariates, right? So let's say now I know nothing about, I have no kids in this school, but I know it's a Catholic school and I know it's high mean SES. So I could take my formula and I could say, what's the expected score for a Catholic school of high mean SES? What's the expected intercept, right? And that would be now that I know it's a Catholic school of high mean SES, that's my best estimate actually of the school mean. I can be a little bit more discerning. In an unconditional model, all I could do is just use the overall mean, right? But the same logic applies either way. So that's one. The other is the observed sample mean, right? So, because I know, like, not all schools are the same, right? So the other sort of competing estimate for a good estimate of the true school mean would be, what's the mean of this cluster? Well, to the degree that I have certain, like, to the degree that I am certain that I have a good estimate of my cluster mean, I would want to place more weight on the observed sample mean, right? If I have a large, and how am I going to have more certainty? I'm going to have a large number of people in that cluster. So if I've sampled 1,000 people in this cluster and I got this mean, and the true school mean is this, right? So imagine they're really different. Here's the true school mean and here's my cluster mean, and I've got 1,000 people in the cluster. Would I want to just plug in the true school, like the like expected overall mean? 1,000 people here saying, no, I think it's way higher than the overall average. That's 1,000 people. I don't think it's going to be this, right? But if I have nobody, I'm going to say this. And if I only have one person, let's say, again, really, insane idea, but let's say I have only one person and that one person, let's imagine it's like an average SATs of the high school, right? And I only sampled one person, and that person had a 1600 on the old school SATs, right? Or whatever it is, perfect math, perfect verbal, right?
It's still 16.
Okay, it's good. Still 1600. So imagine I sample a one person, and this one person has a 1600, and like the overall, mean across all of the schools in Connecticut, let's say, is 1,000. Let's just say, right? Would I want to say, well, I sampled one person from this school, and the mean with that one person is 1600. So I think the school mean for that entire school is 1600. No, definitely not. Now, I only sampled one person and I got a really high score. So maybe I might think the sample mean might be a little higher than the overall average. I mean, that might be a reasonable thing to think, but I'm not going to think that it's 1600, right? So I've got these two competing estimates for what the true mean should be. One is like just basically based on the model, right? And one is based on the information I have from that cluster. The more confidence I have in the information based on that cluster, which is going to be a function of the sample size, the more I'm going to weight the cluster mean in sort of thinking about what the true school mean is. The less confidence I have, because I don't have very much information, to the degree that I'm uncertain, the more uncertainty I have about what this cluster mean is, I'm going to then weight the expected value more, right? Does that make sense? So uncertainty basically gets filled in with our model-based estimates. So as the sample size increases, I have more precision, right, to estimate that true school mean. So there's like less error in the measurement of that true school mean based on the sample mean. So how does this play out? Well, this is how it plays out. The empirical Bayes estimate of the cluster mean. And again, we're going to get these things. We're going to be able to, we're not doing it this week, but we're going to be able to output these things in R. We can look at the actual empirical Bayes estimate of each school's intercept and each school's slopes. So again, we're assuming here no other variables, random effects ANOVA, totally unconditional model, just to keep it simple. But again, the same thing, same logic applies. This empirical Bayes estimate of the cluster mean for school J is going to be the reliability for school J. That's what that lambda is. Lambda is the reliability that I showed you how to estimate before, times the school's actual observed sample mean, so like their OLS estimate or their just plain old descriptive estimate. And that makes sense. Really high reliability, I'm going to weight the observed cluster mean really highly. Plus 1 minus the reliability times the model-based estimate. And the 1 minus the reliability, that's the uncertainty that I have about that cluster mean. So if I have a reliability in a school of 0.99, let's say, the beta sub naught J is going to be 0.99 times the sample mean plus 0.01 times the overall expected value, the overall expected mean. So it's going to be, if you think about that, right? It's basically like I'm right? 0.9. So it's going to give me an estimate. It's going to be really close to the sample-based estimate, right? Because I've basically weighted the sample-based estimate in that example like 99 times as high as the model-based estimate. Do you see what I mean? But now in another school, the reliability might be 0.1 because I don't have very many people in that school. And so I don't have very many people in the school. The reliability is low. So I don't really trust the sample mean as a good estimate of that true school mean. So the empirical Bayes coefficient, like the intercept, right, for that school or the mean for that school is going to be 0.1 times the cluster mean. So it still comes into play. I'm not completely disregarding it, right? But I'm down weighting it. So I'm saying 0.1 times the cluster mean plus 0.9, because it's going to be 1 minus the reliability, 0.9 times the model-based mean. So the more confidence I have in the sample mean, the more I upweight it, right? The less confidence I have in the sample mean, the more I downweight it. And this is part of why I can have these really different sample sizes, and I don't have to have the same cluster sizes, because I've got a way of sort of dealing with it analytically, where I'm saying, like, you give me a lot of information about this cluster, I'm going to use that information. I'm going to trust that information more, right? So I'm going to give more weight I'm going to give more weight when I have more information. To the degree to which I don't have that information, I'm going to basically use information from the model, which is really, if you think about it, information from all the rest of the clusters that are similar to this cluster to kind of like, help me sort of plug that, whatever, sort of plug, you know what I'm saying, like fill in for that uncertainty. Does that make sense? And so you'll hear people talk about these empirical Bayes estimates as shrinkage estimates as compared to like what the OLS estimates would be, which ordinary least squares estimates that you would get from a regular regression. And that's because these estimates are shrunken toward the model-based estimates. The only way that you're going to get the same thing here for the empirical Bayes estimate for like a school mean is if the reliability is 1, right? Which is pretty much never going to happen. And again, the shrinkage is going to depend on how much information you have from that school. So some schools where you have very little information are going to be much more shrunken toward their model-based estimates, and other schools are going to be much, closer to whatever the observed means are. Okay, questions? Yeah. Yeah. I mean, that's a good question. It's still going to work. Obviously, it's going to still work the same way because there's no way that we're going to be able, there's no way we're sort of telling the model, or, we're not telling R like, oh yeah, by the way, this is only a school of 10. But I think that, and I think that sometimes throws people, but I think that another way to sort of think about that is that, like, even if it is a really small school, when we talk about something like a true school mean, it really is sort of like a property of the school, not so much a property of like the aggregation of these 10 individuals. Like if I'm talking about the true school mean, I'm really trying to say, like, is this school a higher achieving school than other schools? And even if there are only 10 kids in a grade level, like you're still like, you know how it is. Well, I was a teacher, like cohorts can be really different from each other, right? So like, this group of 10 kids this year could look really different from the 10 kids next year. And if you're really still trying to extrapolate up to the true school mean, that's not, you still have the same problem, right? Like I would argue in some sense what the problem is you have no ability in that school to get super close to the true school mean, because even if you sample everybody, you're still going to have a small number of kids. Yeah, I know. Okay, so, all right, so moving along. Empirical Bayes estimates. I love empirical Bayes estimates. I think they're really interesting. So I think I've said all of this already. It's based not only on its own data, but it's this weighted average. And we do a lot of weighting in multilevel modeling, by the way. That's a lot of how all of this gets sort of accomplished. So again, I talked about this idea that these empirical Bayes estimates are shrinkage estimates of these coefficients that borrow strength of information contained really in other clusters or groups that are similar. And so the less precise the group specific estimate is and the less variability across groups, the greater the shift is going to be toward the overall group. And obviously we also talked about sample size, right? So the graph here is showing actually, so ML on the x-axis, these are like these, basically, just think of those as like your OLS estimates of your group mean. So just like not your empirical Bayes estimates, okay? Just basic estimates. And the EB on the y-axis, those are empirical Bayes estimates. And what you'll see actually is, again, usually what ends up happening is sort of the further from the mean the group is, the more shrinkage you're actually going to see, right? Yeah. Yeah, sure. So I mean, shrinkage is maybe kind of like, it's a term that people use, but it's kind of a confusing term. Think of this is like, let's just say these are actually what the group means would be. plotted on this dot, these dots, okay? The line, yeah, this line, this diagonal line, right? So imagine these are like the cluster means, okay? Now, these are like the empirical Bayes estimates, let's say. And so, you know, what you see actually is that like for really, for really extreme cases, right, you're actually getting sort of shrunken toward here's zero, right? You're getting sort of shrunken toward the overall, like you're getting shrunken toward the model estimates, which is going to be shrunken toward the overall estimate. So what ends up happening is like, if you have a group that's like again, imagine our unconditional model. If you have a group that's at the mean, right? It's not going to matter how you weight the sample mean versus the overall mean because the group is at the mean. So whether their reliability is high or low, their predicted mean is going to be at the mean because they're at the mean, right? But if you have a group that's like, if the group mean based on this small number of clusters is way, way far away from the mean, so they're really like, you know, way higher than the mean, or they're way lower than the mean, then what's going to end up happening is that these empirical Bayes estimates are going to shrink, meaning that it's going to pull the OLS estimates toward the model-based estimates. That's really what it means. It's sort of like built-in regression to the mean, right? You've probably all learned about regression to the mean in research design, right? In some sense, this is like regression to the mean, but it's regression to the model-based means, right? Like for the same logic, it's actually sort of the same logic and the same rationale. Like I have this really extreme cluster mean based on very few people. I should not just take that at face value and use it. I should say, do I really believe that's a good estimate of the true mean of that cluster? No, I don't. So I'm going to pull it toward the model-based mean. How much am I going to pull it toward the model-based mean? I'm going to pull it more the less certain I am of that cluster mean. So the weighting that I give is actually to maybe is, you know, this is not a great picture from that perspective because you can't see the differential weighting, but the weighting that I give is going to be a function of like the certainty that I have, right? Yeah, Louise. Yeah. And it's so exactly. So what I'm doing is I'm taking these two possible, what I'm saying is there really are two possible estimates of what the true cluster mean is. One is I just take the observed mean. That's what you would have done before today, right? You're like, why can't I just do that again? But life was easier back then. Life was easier, but it wasn't as interesting, right? And so you would have just taken the observed mean, but you would have been wrong because like if you only had a few people in that cluster and you just take the observed mean, there's going to be a lot of error in there, right? So now I'm saying, instead of just taking the observed mean, that gives me some information. Also knowing the model-based mean gives me some information. The more information I have over here, the more I'm going to weight this, and the less I'm going to weight this. Well, I shouldn't be saying this and this on a tape, right? But so the more information I have on the observed mean, the more I'm going to upweight that. What's that formula? It's the reliability times the observed mean. The less information I have about the observed mean and the less sort of confidence I have in it because I have few people, the more I'm going to weight the model-based estimate, right? And the model-based estimate will be weighted based on 1 minus the reliability, right? Yeah. Mm-hmm. I'm going to say I believe it. Right. So if it's a really large cluster and it's got a really like outlier high mean, but let's say the reliability of that cluster is 0.98, then I'm going to take that really high mean, multiply it by 0.98 plus 0.02 times the model-based estimate. So it'll get a tiny bit shrunken. It won't be exactly what it was, but it's going to be a very slight change. But if I had that same really high mean, and I only had like 3 people in that cluster, and so because I only have 3 people in the cluster, let's say the reliability is 0.1 for that cluster, then instead of just taking that really high mean hook, line, and sinker, I'm going to take the really high mean and multiply it by 0.1 plus the model-based mean and multiply that by 0.9, and so it's going to get shrunken quite a bit toward the model-based estimate. Yeah, exactly. Does that? Yeah. Yeah. This is not a plot that's showing all that nuance. I think what I was just trying to show is sort of this idea that empirical based estimates often end up not necessarily being like linearly related to the OLS estimates, right? And that often the more extreme cases are going to get more shrunken. But yes, so don't fret too much about this plot because it's probably not, it's not the most nuanced plot. I had a little extra space. So I looked for something to plug in there that might help, but if it confuses you, just focus on the words. Yeah. Mm-hmm. Yeah. Exactly. And this is why this is such a cool thing. Like if you imagine imagine that you said, I'm going to do this analysis. I mean, there are downsides to what I'm about to say too, which we'll disregard for right now. But imagine you said, I'm going to do this analysis and I'm going to like output all of these empirical Bayes coefficients for the different schools so I can see which schools are high mean schools and which schools are low mean schools, right? Rather than just taking the sample means, I'm going to use these empirical Bayes means. And so if I got a school that looked really high, but it just looked really high because I had only 3 people, right? Rather than saying, oh, that's the school I should go do an in-depth qualitative study of, I'm going to say, like, right? I'm not sure I trust that. Whereas if there's this other school that has 500 people and they have a really high, they have the same height of cluster mean, but it was 500 versus 3, their empirical Bayes estimate of their mean is going to be way higher. And I'm going to say, oh, I trust that this school really is a lot higher than the overall mean. That's the school I should go visit and do my qualitative interviews. Yeah? Yeah.
It's hard, but if we're doing this, so we would get a separate output for each school. So like,
yeah. So we're not going to do this in R this week, but it's really easy to do. We'll do it like next week, probably, or probably next week. What you can do actually is basically, it's going to be like one command and it's going to spit out for every school. It's going to spit out their empirical Bayes estimate just in a big, long, like column vector, which can then actually be attached back to your data file.
like we did with the centering.
Yeah, exactly like we did with the centering. Okay, yes. Pam say we need to move forward. Okay, so estimation of our level 2 fixed effects. We're going to use something called generalized least squares. If we're using REML, we're going to use GLS for the estimation of our level 2 fixed effects. And this is going to weight each group's data by its precision matrix. And again, same idea that we were talking about with empirical Bayes estimates. We're going to take into account the differential precision of the information that's provided by each of the J units. So what we're going to do is when we come up with these estimates of the fixed effects, which are our gammas, like which you should be saying to yourself, like, how do I even get these gammas, right? It's not just we're not just taking all of the cluster means and averaging them, right? Which would, if you think about what would happen if I had a whole bunch of schools and I just took the school averages, I wouldn't be taking into account that there are different sample sizes at each of the different schools, right? So that would be problematic. If I just took the mean of school means, right, I'm not taking into account that some of those school means, well, A, that they're based on different numbers of people, and B, they're estimated with different precision, right? And the other option would be like, well, I just, right, I could just disregard the schools, but that doesn't make sense. It's a multi-level model, right? So generalized least squares is actually going to weight each group's data by this precision matrix, which is really going to be a function of the sample, like the cluster size. So again, what's going to happen in generalized least squares is that when we compute the gamma, those fixed effects, the clusters that have higher sample sizes are upweighted in the estimation of the fixed effects, and the clusters that have smaller sample sizes are downweighted, which is as it should be, right? Okay, so that's all I really want to say about that right now. Maybe I'm going to skip my brief review of maximum likelihood, which is really interesting, but I will skip that. Okay, and we can talk about that maybe next week if we have time. But we're going to use something called maximum likelihood estimation for now. You just have to trust me a little bit because I just, we're going to use these iterative methods, which means we're not going to get all of our parameter values all at once. We're going to sort of iterate back and forth, and I'm going to talk about how that works. There are two kinds of maximum likelihood estimation we're going to use. Full maximum likelihood, or often known as FEML or FIML. And okay, let me just say this right now. I tried to pick FEML. I did try to pick FEML, but you will see it written other ways. So FEML, FIML, and ML are all generally going to refer to the same thing, which is just your garden variety maximum likelihood. The good news is we're really going to use REML, and there's only one name for that, which is REML. So don't fret too much. But in full maximum likelihood estimation, what we're going to do is basically we're going to, for any set of parameters, remember our parameters are our gammas, sigma squared, and our tau matrix. The best estimates, I mean, maximum likelihood estimation in a nutshell is the best estimates are those that maximize the likelihood of observing the data. That's really what a maximum likelihood estimate is. Okay, so in a nutshell, maximum likelihood, we're going to pick parameters that maximize the likelihood of observing the data that we already have. That's really the essence of maximum likelihood, okay? How that happens, don't worry. You can black box it, okay? But that's what it is. So I'm trying to pick parameters that maximize the likelihood of observing the data I have in front of me. And maximum likelihood estimates are both consistent and efficient. What the heck does that mean? Well, here we go. Consistent, and these are terms that statisticians use, okay? So consistent means as n increases, you're gonna sort of get the same value. So you will approach or converge in probability on the true parameter as the sample size goes to infinity. That's really what consistent means, right? So if you had an infinite sample size, you would sort of converge on the true parameter values. All right? Means, and a way of thinking about this is really that with an infinite sample size, our estimates are unbiased. We get the right answer. But consistent doesn't mean I get the right answer in my small sample. Consistent means in expectation, if I had an infinite sample size, I would get the right answer. Statisticians do that a lot, right? Like my expected value, if I, as we go to infinity, blah, 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 asymptotically this and asymptotically that. Okay. So anyway, so that's consistent. So as my n increases, I'm going to converge on the true parameter values. And that, again, think of consistency as really relating to bias. I'm going to get the right answer, right? I'm not going to have biased estimates. Efficient means, okay, these are going to be the estimates that give me minimum variance, which is a good thing too, right? I want to minimize the error in my estimates. So something that's asymptotically efficient is going to be, let me say this, maximum likelihood estimation is asymptotically efficient. So given a large sample of the data, we should get approximately unbiased estimates with minimum variance. So that's all good stuff. Okay, great. We like that. When you're estimating a multi-level model with maximum likelihood, oh, and by the way, this McNeish paper, Dan McNeish paper from multivariate behavioral research is, I think it's called something like a colloquial elucidation of estimation techniques in multi-level modeling, and it really is. So if you want to read more about maximum likelihood and restricted maximum likelihood estimation in a paper that you can actually understand rather than going into like a stats journal, I highly recommend this paper. It's really good. Yeah, I might have made, yes, it is. I agree, but it is actually, it really is readable. So anyway, so when we estimate multi-level model with maximum likelihood, the variance components and the fixed effects are actually going to be estimated simultaneously. So they actually are somewhat dependent on each other. Okay, so what ends up happening is like we estimate the fixed effects and the variance components within the same algorithm, but in sequential steps. So like the fixed effects are estimated, then the random effects are considered missing, then the variance components are estimated based on the fixed effect values that you had in the prior iteration, and the variance components are then used to update the fixed effects estimates in the next iteration. You go back and forth, and this is what the computer is doing, okay? It's going back and forth and saying like, okay, here's some fixed, and it starts usually with OLS estimates for the fixed effects as its start values, because that's like a good place to start. And it goes back and forth until basically between iterations, you're not getting any changes in those parameter values. And once those changes are really, really small, that's what we mean when we say that the model is converged. That like basically, I don't need to iterate anymore because I keep iterating and I keep getting the same values for my parameters. So I'm done. Yeah? So that's a good thing. Okay. So what are the limitations of just your garden variety maximum likelihood? Well, the estimates are conditional on the point estimates of the fixed effect.
Here's what I found.
No, I'm not talking to you. And so that means that I'm actually, because the estimates of the variance components are conditional on the point estimates of the fixed effects, then the variability in the fixed effects estimate is actually ignored, right? And you're also consuming some degrees of freedom to estimate those fixed effects, and you're not accounting for that. So those are kind of the two issues with regular maximum likelihood. Now, and this ends up being not a big deal if you have a large sample size, because just the same way that this is very analogous, by the way, to, do you remember when you were in Quant 1 and you learned about variance? Yeah? So what's the formula for a variance? It's the sums of squares in the numerator. What goes in the denominator for a formula for the variance? N or n minus 1? Well, which is it? Is it n or is it n minus 1? Depends on if it's for a population or sample. That's right. So it's sums of squares divided by n for population, right? Sums of squares divided by n minus 1 for sample. Why? Why the heck do we do that? Does anybody know why do we adjust the formula for the variance? So that's what they told us to do. Yeah, and we're trying, like, we know, and again, we know that, like, again, asymptotically and in the population, that, the maximum, it turns out that the maximum likelihood estimator for the variance is, again, I'm just talking about a simple model where we're estimating the variance using maximum likelihood. It's the sums of squares divided by n. And, that works in large samples, but remember what I said about sort of consistency, right? There is, if you have a small sample, there's some degree of bias actually that's introduced. And so, and we sort of need to take into account degrees of freedom, yada, yada, yada. So we use the n minus 1 because that's actually going to give us an unbiased estimate of the variance in a small sample or in a finite sample. No, I guess not. Okay. Give me 2 minutes to wrap this up. Yeah, so now I forget what I said. So the variance, so the maximum likelihood estimate for the variance, which is this over n, it is really just like, in the this is like asymptotically, whatever, like this is what it should be, but we have a finite sample. So we actually need to make a correction for our finite sample. And so we use n minus 1, which is that's an unbiased, it's a less biased estimator of our variance. It's not the maximum likelihood estimate. It's the Remel estimate, actually, of the variance is n minus 1. I mean, it's totally analogous. So, we don't take into account sort of with maximum likelihood. We're not sort of taking into account the fact that we have, this. We're not adjusting for the uncertainty about the fixed effects. So, okay, give me 2 minutes, and I promise. So Remel kind of works a little differently. It estimates the variance of the components with no fixed effects, and then it estimates the fixed effects through generalized least squares, right? Weights by precision, as we already talked about. And, the GLS fixed effects estimates should be the same as the maximum likelihood estimates, as long as, provided that the covariance structure of the observations in the clusters is known. So that's fine. It turns out that, both of these techniques are using this iterative process, but maximum likelihood is like bouncing between the variance components and the fixed effects until we meet convergence. And the REML is actually just estimating the variance components until convergence, and then it estimates the fixed effects as a final step with GLS. So it's, accomplishing the same thing in two very different ways. And you might be thinking, why do I care about this? Maybe I should not have made such a big deal about this, but it is actually going to matter when we do model fit. It's going to matter quite a bit. So you might be asking yourself too, how different might I expect these estimates to be? And it turns out that where you're going to see deviation is really generally not in the estimation of the fixed effects, unless you have a really, really, really small number of clusters. But generally speaking, if you have a large number of clusters, you're going to get basically similar results, whether you use FEML or REML. And it's when the cluster size is large, not whether the overall sample size is large. What's really salient here is the number of clusters. If the number of clusters is small, the full maximum likelihood estimates tend to be smaller than the REML estimates for the variance components, and they are downwardly biased in the same way that, remember we talked about the variance dividing by n versus dividing by n minus 1. If you have a small sample size and you use the formula that has n in the denominator, right, you're going to get a smaller variance, right, than if you use n minus 1. Is that right? I think so. So same kind of thing here. So our FIML estimates for the variance tend to be smaller than the REML estimates, and the REML estimates should be more accurate. So the FIML estimates are biased in small samples. And the question is, how biased are they? Now, this is just an approximation, okay? But it gives you a good sort of feel for it. If you want to get a sense for the approximate amount of bias you might expect, you take the number of clusters minus the number of fixed effects, so that's what J minus F is, and divide it by J. And where you're going to see these problems, generally speaking, is in the tau matrix. Again, until the cluster size is really, really small, you generally don't have to worry about bias in the fixed effects, but where you see the bias is in the variance components. So we can kind of get an idea of how much those FIML estimates might be downwardly biased. For all of these reasons, REML is the default estimator in LME, like Elmer, LME4, and pretty much every other multi-level package, I think, or almost all multi-level packages. REML is the default. And if it's not the default, it's available. So all of the models that we have estimated so far, we've used REML. And you would think, okay, then why did I need to know about FIML? Who cares? But the reality is that when we go to compare models that differ in their fixed effects, okay, if you want to compare two models that differ in terms of the variance components, so I've eliminated a random effect, let's say, I can compare those two models using the deviances that I get out of REML. But because of these differences I just talked about in terms of how the models are estimated, if I want to compare two models that differ in terms of their fixed effects, so I've added a variable, like sector or something to my model, and I want to compare the fit of those two models, I have to compare the fit using the deviances that I get through full maximum likelihood estimation, FIML. So even if you're using REML because you want to get better estimates of the variance components, the minute that you step into this model fit world and you want to compare two models that differ in terms of their fixed effects, you need to compare the two models' deviances using FIML. And the deviance is really just the -2 log likelihood that comes out of this maximum likelihood estimation. And a smaller deviance is better. So we'll get this deviance. We don't get a chi-square the same way we do in SEM, but we get deviances, and we can compare two deviances from two different models the same way we compared chi-squares from two different models. But in this case, I didn't have this in SEM, this whole issue of like, I just did everything with maximum likelihood estimation. And now the reality is that like by default, I'm using restricted maximum likelihood estimation, and I'm going to have to be very careful to make sure that if I want to start doing these deviance comparisons, that I compare the deviances of the two models that were generated. The deviances were generated using full maximum likelihood estimation. The good news, by the way, and then I will stop and give us a short break. The good news is when we use the ANOVA, I'm going to show you, we're going to turn over to talk about all this stuff in R after the break. When you use that ANOVA command in R, if you've estimated the model in REML, it will re-estimate the model using FIML, and it will use those deviances. So it's smart enough to do that for you, which is really, really nice. But there are other times where you might, like, you know, where you're not using the ANOVA command and you're just doing it yourself. And so you need to know, like, you know, and, you know, what are you comparing, right? Okay, break. Let's take a break. 5 minutes. 5 minutes? 5 minutes.
Yeah.
Good morning.
Yep.
Okay. Ready to roll? Okay.
I can move this along.
Okay, I am gonna skip testing the liquid. I'm gonna skip degrees of freedom. I'm gonna skip that. I'm gonna skip that. Okay. Okay, let's get started again. I want to spend just a few more minutes on the PowerPoint and then turn our attention to the R Markdown. So I'm going to skip over the test of fixed effects stuff for right now, because I think we can come back to that. It's not on the homework, and it's, you know, relatively subtle, but not as important. So I want to talk about this issue though. When do we include random effects? Because this is like, you know, if I had to pick some of the, like, what's one of the fundamental issues in multi-level modeling is like, when should I include the random effect for the slope? I mean, not the intercept, that's usually kind of a duh-he, but like, should I allow these slopes to be randomly varying or not? It's like the $1 million question in multi-level modeling. And there are a fair number of complexities that we have that make it, you know, that make it not totally straightforward. Okay, so the first thing is, you know, if we, you might not have noticed, but, you know, in LME4, you don't even get test of statistical significance for the variance components. And that is deliberate. Doug Bates does that by design. He doesn't, because computing standard errors for variance components is not so straightforward. Why is computing standard errors for variance components not so straightforward? And, well, no, I mean, that's not a good guess, but think about variances, right? Like first, look at the test, look at the hypothesis test. We don't test that the variance is like 0 or not 0. Variances can only be positive, right? So we're testing whether the variance is 0 or greater than 0, which means that the null hypothesis, and this, I won't belabor this too much. I could wax poetic about it, but I'll try to move through it quickly. But it means that the variance is on the boundary of the parameter, I'm sorry, the null hypothesis is on the boundary of the parameter space, right? If I set up this null hypothesis, and so this is not just the same as like one-tailed versus two-tailed. I mean, it's a one-tailed test, but in a one-tailed versus two-tailed test, when you're like, is the mean difference 0 or not 0? The mean difference could be greater or less than 0, right? But in this case, variances can't be less than 0. So I've set the null hypothesis to say, right, the variance is 0, but the variance is 0 is actually the, like, what I mean by the boundary of the parameter space is that's the lowest the variance could possibly be. It's sitting there, right, on the border of like not admissible, right? You get a negative variance, if you remember this from SEM, you get a negative variance, that's a no-no, that's not admissible. So to test a variance for statistical significance is actually way more complicated than testing other types of parameters. And the first thing, so this boundary parameter space thing is an issue. And so it means, you know, first thing is, it means we shouldn't be using any kind of two-sided tests, right? So often programs will sort of report two-sided p-values, and that is wrong. But, you know, the second thing is just that, like, how the standard, just take a step back and say, we usually say that the statistical test is the parameter divided by the standard error, but analytically, standard error formulas usually rely on normality, right? They sort of assume a normal distribution. But if you think about what the distribution of a variance would be under the null hypothesis, let's say, right? Maybe under an alternative hypothesis, the distribution could look normal, but under the null hypothesis that in the population, the variance is 0, what would the sampling distribution look like? Well, it wouldn't be normal, right? It would be very positively skewed. And so that makes computing standard errors for these variance components, you know, questionable, right? Very questionable. So I think, you know, when you read the multi-level literature, most people will say, not, you know, not so sure you should trust the standard errors for variance components. So some programs sort of output them, but people don't really trust them, and other programs don't output them at all. And there are a variety of ways that people have sort of come up with to kind of think about how to determine whether these variance components are you know, necessary. So another thing to kind of consider is if you put in randomly varying slopes that you don't need. So if you put in randomly varying level 1 coefficients, I'm saying slopes because usually the intercepts are fine. It could technically be the intercept, but you know, if you try to estimate all the potential random effects in your model, and you have a very large model, and I think I said this before, that can be really problematic because you're trying to, that is true. Now you're trying to estimate this really complicated tau matrix, so that's difficult, right? But also, like, it's made even more difficult if one of those variances is really 0 in the population, right? Because that makes the problem even more difficult. And so if you allow slopes to randomly vary when they're actually 0, that will greatly increase your likelihood of getting either a totally non-convergent solution, so you don't even get any results, or to get results, but to get some sort of an error message. So allowing, you know, just sort of by default, allowing all of your slopes to randomly vary is not necessarily, if you have a lot of slopes, right, is not necessarily good practice. And so we really have to think about, like, how do we determine which slopes we should have and which slopes we shouldn't have? One thing I will say is that if a model is really, really slow to converge, that actually can be somewhat diagnostic of, it can be an indication that you've got a slope that you're saying should randomly vary that really should not randomly vary. So, so non-convergence or slow convergence can be one sign that you don't need that random effect. But unfortunately, if you imagine you have like 6 randomly varying coefficients in the model and it's really slow to converge or it doesn't converge, that tells you there's a problem with one or more of them, but it doesn't tell you which one, right? So that's another problem. So that's diagnostic, but might not be helpful if it's a really large model. So, okay, I put these little green dollar signs there because I said, like, this is the money question. Like, this is a question. Yeah, exactly. That continues to rear its ugly head, and one where there's continues to be a lot of research currently being done in multi-level modeling. Like, how do we know whether we should include random effects or not? Which is really, again, a question of whether to estimate these variance covariance components. One option is to look at model fit and to look at these likelihood ratio tests. Now, the complication here is technically, the likelihood ratio test needs to be adjusted when you're dealing with variances because of all the reasons that I just said before, okay? And I'll talk about how we can adjust those for a second. Another possibility is to look at model adequacy, like does adding this randomly varying slope, how much variance does it actually explain? Like if I add this randomly varying slope and it explains no variance in my model, like maybe I don't need it, right? So, thinking about that is a good idea, but again, it's more complicated in multi-level models. Tests of statistical significance, as I said, can be really problematic. Rodenbush and Breich implement a chi-square test in HLM, but as far as I can tell, it's not available in LME4. Obviously, substantively, you should, not for homework necessarily, because this isn't your research, right? I'm going to tell you whether you should start with a random effect or not, but in real life, substantive considerations are key here. Before you estimate your model, you should be asking yourself, do I think this slope needs to randomly vary or not? And you should have a clear substantive justification. You shouldn't just default to like, oh, I have 10 independent variables. I will let them all randomly vary. That's like a recipe for disaster, right? So you need to ask yourself, like substantively, what do I, and so again, you should be thinking about this before you ever run your model. And then finally, like, this is a place where logic and common sense are going to be super, super, super important. Okay. About logic and common sense? Okay, sure. Go for it.
Yeah, I know it's not on the syllabus, but I was just curious before the works for one of the models, and I did notice that it seemed like the random effect significantly added to the degrees of freedom. I was just wondering, like, is that the variance components that are doing that, or is?
Well, yeah. When you add a random effect, so, and I think we talked about this last time, like if you, let's say you just have a model where you have a randomly varying intercept, and now you add a random slope, right? You're actually adding parameters. So you're adding two parameters there because you're adding the variance for the slope and the covariance for the slope and the intercept. And obviously the tau matrix, this unstructured tau matrix, the more random effects you have, the more parameters you're adding, because if you already have 5 random effects and you add a 6th one, you're adding the variance plus you're adding the 5 covariances with the other 5 random effects, right? So yeah, so it can really kind of blow up how many parameters you're adding to the model just by adding one random effect. One random effect does not equate to like 1 degree of freedom.
Right. And so degrees of freedom in that context refers to the number of parameters.
Yeah, well, what we'll really think about degrees of freedom in terms of difference testing, like we'll talk about estimating the number of parameters, but then the degrees of freedom are really going to be the difference between the two models in terms of the number of parameters. So that's that. The degrees of freedom is going to be sort of comparative. Okay, so moving along. So again, the deviance is the -2 log likelihood, and deviance is this measure of model fit, but it's really a measure of model misfit. So the smaller the deviance, the better. You cannot say anything about a deviance in isolation because it's a function of a lot of things, but you can use it comparatively to compare 2 different models. So, if you have a model, it's not like chi-square and SEM, where you're like, oh, you don't get a chi-square in degrees of freedom. Like, oh, my chi-square is 300 and my degrees of freedom are 10. That's bad fit. You don't get that. You just get my deviance is whatever. And there's no way to actually interpret that from a single model. The only way to interpret deviance is in a comparative framework, like comparing one model to another. But again, comparing one model to another, the higher the deviance, the worse the model fit. But like, what if it's just a tiny bit higher? How much higher does it need to be to say that the model is misfitting? Well, that's what we're going to talk about. Okay, so let me say something about nested models too. And this is going to, again, just trust me on this for today. In a very deep way, this is actually the same as SEM, but it's going to seem different right now. And let's not go there today because we need to actually get to the homework. But here, 2 models are nested if the parameters from one model are a subset of the parameters from another model, right? So that means if I'm adding parameters from model A to model B, those 2 models are nested. Or if I'm subtracting parameters from model A to model B, those parameters are nested, okay? I mean, not parameters, those models are nested, right? And we have a reduced model that has fewer parameters, and we have a fuller model that has more parameters. And the important thing here with nested models is, so if I'm just adding parameters, add, or if I'm subtracting parameters, delete, those 2 models are going to be nested. But back to like middle school science, if I add a parameter and I take away a different parameter, right? Those two models are not nested. And it makes sense if you think about it, because I've added some complexity over here, but I've made something simpler over here. And it's like you've got two independent variables varying at the same time. How are you ever going to be able to really parse out which thing is making the model fit, right? Like, because adding a parameter should make the deviance go down, but deleting a parameter should make the deviance go up, and you're only going to get two deviances, and there's no way to parse it out. So you always just need to make sure that when you're building models and you want to compare them using chi-square difference test or likelihood ratio test, those are synonymous, that you are building models where where one set of parameters is a subset of the other set of parameters. And that,
Yeah, safe to say the level 1 models should be the same always when they're nested, or could you?
No.
I'm trying to think of when could.
well, I don't know. I mean, not necessarily, because you could have one model could have SES in as a level 1 variable, right? And the other one doesn't. They would still be nested. So it's really that you could get from one to the other either by adding stuff or subtracting stuff, but not both. If you need to add and subtract to get from one model to the other, they're not necessary. Okay. So imagine we've got like a base model nested in an alternative model. So we've got a simpler model and a more complex model. I'm going to get a deviance for each model. That's what the D0 and the D1 are. And I can just take the difference in the deviances. I just literally subtract the deviance of the simpler model. I'll take the deviance of the simpler model minus the deviance of the more complex model. And that makes sense because the deviance of the simpler model is always going to be bigger, because as I add parameters, the deviance is always going to go down, right? So I take the bigger deviance, which is going to be the simpler model, minus the smaller deviance, which is going to be the more complicated model. And the difference between those two deviances is going to be chi-square distributed with degrees of freedom equal to the difference in the number of parameters that you're estimating in the two models. So for example, if I have a model where I have a randomly varying slope in model 1, in one model, and I take out that randomly varying slope in the other model, the difference in the number of parameters is going to be 2, because I'm taking out this, I'm not allowing the slope to randomly vary, so I'm actually eliminating a variance and a covariance, right? And I can just look at the difference in the deviances, and I can compare that. I get some sort of a deviance difference, and I'll look at that and compare it to the critical value of chi-square with 2 degrees of freedom. So again, this is very similar to what we did in SEM class, right? But the difference is that we're using deviances now instead of using chi-squares, but the actual difference testing follows the same logic. We've got, now, great, super easy. But technically, and I won't belabor this too much, but technically there are some complications when you use these likelihood ratio tests to compare the variance components. Because the variances, again, we've got these boundary constraints and everything. So technically, you shouldn't just be using like the regular old chi-square to compare two models that differ in terms of variance. It gets even more complicated than that, though, because it's totally fair to use the garden variety chi-square for the covariance term, because covariances aren't bounded at 0, right? A covariant, like correlation can be positive or negative. So if the null hypothesis is that the correlation is 0, you're not sitting on the boundary, but you are with a variance. So this is really probably nitpicky. So, well, this part's not nitpicky, but so again, the likelihood ratio test gives us whether the simpler model, once we do this, once we subtract the deviances and we get the degrees of freedom, it tells us whether the simpler model fits worse than the more complex model, or if the more complex model fits better than the simpler model, right? So if the chi-square difference, if the deviances between the two models are not statistically significantly different from each other, we're going to favor the simpler model, because basically the model fit has not degraded much by eliminating those parameters. So we're going to favor the more parsimonious model. If, on the other hand, if the deviance drops a lot when we add those parameters, right? So the more complex model fits a lot better than the simpler model, then we're going to favor the more complex model. Again, same logic as SEM class. But again, you can't compare the deviances that you get under REML unless you're comparing variance covariance components. So you can't compare two models that differ in their fixed effects using the REML deviances, but you can compare two models that differ in terms of their variance components using REML. Sure. So if you're going to, you can compare two nested models that differ in their fixed effects, their random effects, or both, right? If you're comparing two models that differ in terms of their random effects, i.e. their variance components, right? Like, so you've changed the random effect structure, which changes the structure of your variance covariance matrix. You can compare, if that's all you've done and you haven't messed with the fixed effects, you can compare the deviances that are generated using REML. It's not a problem. But if the two models also have differences in terms of their fixed effects, which means like you added a parameter, let's say, or eliminated, added a variable at level 1 or level 2, right? Or eliminated a variable, and you've got fixed, more or fewer fixed effects parameters, then you need to use the deviances that you get under FEML. So you can compare the deviances of models that have some differences in their fixed effects. And if the models are not nested, so you've changed stuff like you've added and deleted, then you can't use this chi-square difference test at all. Then you need to use like AIC, BIC, that kind of stuff. We're not going to really talk, we'll talk more about that next week.
In default for the homework, though, if they're comparing two models, should they just use the ANOVA command, which will?
Generally, yeah.
Yeah.
Okay. You said that will, in R, it will do it for us.
Yeah.
In R, the ANOVA command will adjust. I mean, it will actually run the FIML. It will give you the FIML estimates, right? So you don't have to worry. It will rerun the model as FIML and get the deviances that way. Yeah.
Benchmark or like
Well, so it's the critical value of chi-square with degrees of freedom equal to the difference in the number of parameters. So if you have a 1 degree of freedom test, what's the critical value of chi-square? 3.84, right? If you have a 2 degree of freedom test, what's the critical value for chi-square? 5.99. Yeah, and the 3 degree of freedom test is 7.8 something. But you know, you can always look that up online. And actually, you don't even have to, because the ANOVA test is going to give you the p-values. Like it's gonna compare it to the critical value and give you the p-value. So you don't actually have to know all the critical values of chi-square. Okay. Okay, so here we go. So the likelihood ratio test for variance components, again, technically, the chi-square distribution doesn't really apply in the same way when we're testing variance components because the null hypothesis is on the boundary of the parameter space, which means you get a p-value that is actually like bigger than it should be. So if you don't take this into consideration, actually, your results are conservative. Like you're going to end up failing. You're going to end up saying you don't need a variance component when maybe perhaps you do need a variance component. Okay. So as a rule of thumb, if you just have like a randomly varying intercept and you were doing a chi-square difference test between a model that had a randomly varying intercept and one that didn't, you could just, one thing you could do is just have the p-value. Like if you got something, you just cut it in half to kind of take into account the fact that it's a variance, right? And so that will actually adjust the p-value. But we're not usually comparing a model that has a randomly varying intercept to a model that doesn't have a randomly varying intercept. We're usually comparing two models that differ in terms of their slopes. So again, that's more complicated because, you know, again, we've got this tau matrix, right? And so really, this variance parameter should be adjusted, but all of these, it's totally fair to use the regular old chi-square. So what you end up with is like a mixture of chi-square distributions in terms of like what you should really be using for your test of statistical significance if you're like eliminating a variance component or not. Okay, now I'm kind of making a big deal of this, but the good news is So I'm going to show you a table first that kind of gives you the critical value for eliminating a slope variance and covariances simultaneously. Let me show you that. Okay, here it is. And this is from Snyder's and Bosker, 2012. So P here is the number of random slopes in the model, including the one you're testing, but excluding the randomly varying intercept. So here where it says P is 1, this is like a model where I want to know I have one randomly varying slope and I'm either going to like have it in or out, right? And because the critical value, because of everything I already said, the critical value here, here we go. The critical value actually at 0.05 for this mixture, this is a 2 degree of freedom test. Let me point that out because again, it's eliminating a randomly varying slope. So I'd be getting rid of a variance and a covariance. So I said actually that 5.99, that's like the critical value of chi-square with 2 degrees of freedom, right? Do you remember that? Yeah. But this is saying technically, and again, like, do you lose sleep over these things? I maybe do, but maybe I shouldn't. Technically, the critical value of chi-square should be 5.14, not 5.99. And that little adjustment down is because it's totally fair to use the regular chi-square for the covariance component, but it's not totally fair to use the chi-square for the variance component. So we adjust down to 5.14. If I have like 2 slopes, and it's like, now it's a 3 degree of freedom test because I'm going from 2 slopes to 1 slope. Instead of using 7.8 something, I should be using 7.05. Okay? And so all of these values are like a little smaller than the critical values of chi-square. So, okay, so that's true and that's correct. Yeah, so here I've got it on this slide. Here's the traditional 0.05 level. Here's the technical 0.05 level that you should be using to compare these models, which by the way, none of the packages do. But you can see like this is really subtle, right? So how does that like transfer into a p-value? Well, the reality is like here, the p-value really, like again, is anything less than 0.0765 should be statistically significant, right? Because really I should be using 5.14 instead of 5.99. Do you follow my logic? So like if I got a p-value, if I ran this ANOVA and I got a p-value of 0.06, technically, it really should be statistically significant. And here you can see like, this would be really the threshold for the p-value is 0.07. And here with this, with randomly varying slope where I already have like 3 slopes in the model, the p-value would be 0.0674. And you can see, by the way, this p-value is getting closer and closer and closer to 0.05 because again, it's a mixture of, for every covariance, the chi-square is fair, but just for the variance, the chi-square is problematic. So it makes sense that these are getting close. Okay, so what do I say to all this after I've dragged you through all of it? The first thing I would say is you don't have to worry too much about this, right? Because if you look at this chart, you can say to yourself, the only time that this is going to make a difference is when I'm sitting between 0.05 and 0.077, right? That's the space where you should be. And so you should, I would argue, ask yourself, if you're in that space, you should be using other criteria besides statistical significance to begin with. And especially if you find yourself in the space between 0.05 and 0.077, like I think that in general, 0.05 is a very arbitrary threshold. But like, if this lecture should convince you of anything, what I'd like it to convince you of is that 0.05 is an even more arbitrary threshold when you're talking about variances, because 0.05 isn't really even 0.05 anymore. So what I would say is the vast majority of the time, 99% of the time, you're not going to get a p-value that's between 0.05 and 0.077, right? So if your p-value is less than 0.05, it's significant. If it's greater than 0.08, it's not significant, right? If it's somewhere between 0.05 and 0.08, I would encourage you to not just like, you should think more deeply about what to do if you find yourself in that little corner of p-values. Does that make sense? And not be like, oh, it's 0.06. I clearly don't need it, right? You should come up with another rationale as well, right? You should be thinking about it conceptually and in terms of variance explained and other things. Yeah. The P123, this is like, I have one slope in the model and I'm going to eliminate it or not. I have two slopes in the model, I'm going to eliminate one of them or not. I have three slopes in the model, I'm going to eliminate one of them or not. And that's why this is the number of degrees of freedom in that test. Yeah? Okay. So, okay. So let us, well, let me just say, yeah. So this Datic MLM package that I had you all install, that can actually allow you to kind of look at the variances and the covariance separately to see whether things should be eliminated. It breaks this omnibus test into pieces. It currently only works for one slope though. The nice thing about the Datic MLM thing, the nice thing about the Datic MLM procedure is it's the only one that I know of that actually takes into account this mixture of chi-squares. The ANOVA and the RANOVA stuff that we're going to talk about, they all just use like, they're not making this distinction. But again, you can use something that doesn't make this distinction as long as you are thoughtful about what happens between like 0.05 and 0.077. Okay, so let me stop there because I definitely want to make sure we get to our R stuff, right? I don't want to save anything. So let us turn to R. And if you go to week 4, remember to save this in a folder on your computer, right? You're going to find an R markdown file. And I'm going to open that. So week 4 in the courses folder, or it's week 4 in your, Husky CT. Okay, here we go. By the way, let me say just a couple things about R Markdown, because I guess people are kind of confused about R Markdown. Install, sure, is all that. Okay. So in R Markdown, right, what I'm doing, I can write any text I want in the white spaces, and then to like, where I put the R code, I always have these little 3 hash marks, and then in brackets R. Sometimes I have these comments, those don't really matter. We don't have to worry about those. They just allow you to like include or exclude stuff or whatever, but you have to have like hash, 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 R, right? And then these, hash, 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 bracket, R, bracket, and then hash, hash, hash on the bottom. There's actually a button up here that's really nice. See this plus C, the green thing? If you press on that, it will give you, it'll give you that, which is kind of handy. So you don't have to like, so if I go like this, right, I can go, I click on R, right? And then it actually just gives me that. And then I can just write my code in there, right? And then the next thing, I mean, again, you don't have to use R Markdown, but the nice thing is it's really easy to comment above and below your code, right? And then at the end, when you want to knit something, you hit knit. Now, you've had errors when you knit. You're not alone. Everybody does. There is a way to override that too, but like you can knit into Word, PDF, HTML, and yeah, there's, sometimes you'll hit errors or whatever, but that's the knit button. But anyway, okay. So let's go ahead and we need to do a couple of things here because everybody has the handout, right? Okay.
No, I didn't do the handout.
Oh, okay.
What? I was daydreaming, sorry. My
So
bad.
I'm just gonna like, right now, while the handouts are going, I'm just like clicking to attach all of those libraries. There's a little line here in case you ever want to turn off your scientific notation, which I find super annoying, although you'll get a lot of zeros on some of your p-values now. You can just say, options, psi pen equals 100, and that'll turn off your scientific notation. And then, actually, I'm not, I've already, I think, installed all of this stuff, so I don't have to worry about that. Okay. Actually, I also put some functions in here in case people don't have the Datic MLM stuff up and running. So go ahead, and each of these things is just a function that I wrote. You can literally, well, some of them Randy, a couple of them Randy wrote, some of them I wrote. You can literally just copy this, you know, and put it into your text if you ever, or not text, into your code if you ever want to. So this one's an ICC. This is the Roddenbush at R squared at level 1, Roddenbush R squared at level 2. The intercepts, R squared slope is for the slopes. Okay. Here we go. So I'm just going to go ahead and attach those in case we need them. And then this one, oops, R squared slope. And then this final one is R squared RB, actually is more general that you can use for slopes or intercepts. So, okay. So right now, all I've done is just kind of made those so that they're available. We're going to use the same old data file we've been using. So I'm going to just call my data. There it is. Great. Okay, where am I? Here we are. Okay. Here I'm gonna make my school ID a factor. By the way, notice here, I'm not making sector a factor. And that's because if you do, you'll have, again, you don't have to worry about this for this week, but you'll have trouble with that R squared measure, the Wrightson-Sturba. Doesn't deal well with factor variables as variables in the model. Okay, model 1 we don't really need, but I will run it anyway. I need to center my predictors. So this is all code that you've seen from before, but again, I'm just getting us up and running so we have the variables we need. Okay, I didn't really want to do that, but I did, I guess. Okay. Here we go. So now we're finally, I want to start with model 6 because this is this model. If you look, see, this is what I hate about when you're looking at Markdown. If you look on your paper, this looks horrible. But if you look on the thing that I handed you, you can see that this is actually really pretty equation showing you what model 6 is. So take a look. Is there an extra one of those, by the way? Any chance?
I handed them all out.
Okay, that's fine. Okay, send it back up. So take a look at model 6 here. So model 6 is this full contextual model where I have SES centered around its group mean, and I have mean SES, which I've centered around the grand mean, okay? And now I want to look at what would be called a contextual model or a slopes and intercepts as outcomes model. And I've got sort of level 1, level 2 in the combined model. Okay, so let's see. Let me turn to this page. So you should be able to, so everybody sort of with me. So we've got sector, so we've got SES is group mean centered, right? I'm going to allow a randomly varying slope for SES. I can see that because I've got the U sub 1J. I'm allowing a randomly varying intercept. I can see that with the U sub naught J, right? And then the question is, what's the structure of the tau matrix? And in model 6, I'm going to estimate the covariance between the randomly varying SES slopes and the intercepts. Okay? So unless I tell you otherwise, you should always default to an unstructured tau matrix. And I think, I think that's really important because it turns out, if you don't, well, okay, think about this. What's the covariance between the slope and the intercept? It depends on where the intercept is, doesn't it? Right? I actually had a slide in there in the PowerPoint. If you look at the PowerPoint slides, slide 47 in the PowerPoints. If you look at slide 47 in the PowerPoints, it's just a little silly picture, but notice that, just imagine everybody here has like the same intercept at this one point, right? And then the slopes actually fan out. You see that? So think about, I could center this right here. If let's say this is where I'm centering the intercept. Would there be variance in the intercept if I centered right here? No, right? There'd be zero variance in the intercepts. Would there be a covariance between the intercepts and the slopes? Well, if there's no variance in the intercept, can you have a covariance between the slopes? You can't, right? You can't have a covariance between the slopes and the intercepts because there's no variance in the intercept, right? So if I were to center here, my tau naught would be 0, and my tau naught 1 would also be 0, right? So in that case, it's fair to have like a covariance of 0 because there is no covariance. But what if I were to center out here? Let's say my centering occurs here. What would the covariance between the slopes and the intercepts, would it be positive or negative or 0? I mean, imagine these are the intercepts. People with higher intercepts have flatter slopes, right? Well, this is kind of a trick question, and I didn't mean it to be a trick question, but if you think about it, the slope is negative, right? So, but what's the correlation between the slope and the intercept? If you look at it, people with again, assuming I'm centering here, people with higher intercepts have less negative slopes, which means they're more positive, which actually means that this would be a negative slope and a positive correlation between the slope and the intercept. Because flatter actually means more positive. I know, this is like a brain teaser. And again, that didn't make sense today. Don't worry about it because we'll go through that again with longitudinal models. But the point I'm trying to make is it wouldn't be 0. That I would expect you to get. The covariance, if you were to center here, is not going to be 0. The covariance, if you were to center here, is going to be 0. So the thing is, if you constrain the covariances in that tau matrix to be 0, like that's what that covariance is. It actually varies as a function of the way that you're centering, right? So like if you're constraining it to be 0, then you're like saying no matter how I have the model set up, I want that covariance to be 0, but the covariance is a function of it's a function of those variables and it's a function of the model. And if you constrain it to be 0 and it shouldn't be 0, then that's a misspecification of the model, which can actually have an effect on your parameter estimates. Now, if you constrain it to be 0 and it really should be 0 or something close to 0, no problem. But if you constrain it to be 0 and it shouldn't be 0, it should be something, radically different from 0, you've now introduced a misspecification to your model that can, again, with maximum likelihood estimation, misspecification can actually sort of it's not, because we're sort of estimating everything all at once, it can, cause problems in other parts of your model, not just there. So, yeah. So we're always gonna, what's the structure? We want to estimate the covariance is what I'm saying here. Okay. And just another point, here's the model code for this contextual model. And you can see that I haven't said anything about the main effect, but in LME4, if I specify these cross-level interactions, the main effects are understood to be there by default. So like here, I'm saying model 6, math achievement is a function of, okay, the SES slope, right? And it's the effective sector on the SES slope. But again, the effective mean SES on the SES slope. And I haven't said the effective mean SES on the intercept, the effective sector on the intercept, and just sort of the intercept of the SES slope. But, in LME4, as soon as I put in those interactions, it's going to put in main effects for all of those things. So you can write all of that out if you want. You could say, I could actually put in, I could do this. This is the way sector plus You know, mean SES.
You've got a breadth.
Plus, there we go. So, right? Yeah, here you don't need the 1 because you do need it if you don't have a randomly varying slope. But as soon as you have a randomly varying slope, you could actually get rid of this too. So there are like a lot of different ways that you can write the same code. So anyway, this is going to give us the same results that we would have gotten. You know, you might find it helpful at this point in your multi-level career to actually write things out the long way, just so you see it all, but you know, you don't have to. I'm gonna put the 1 back in there. Okay. So now let's run model 6. And let's get our summary. I think a really important thing. Okay. Yeah, fine, no problem. Okay, so maybe now you might be saying, maybe I should go back to scientific notation, because look at all the zeros in my p-values, but I don't know. I don't like
I
scientific.
like this better too. I always get rid of it.
I know, I do too. So, okay, so here what I want to do is make sure that you can actually interpret all of these things, right? So this is a full contextual, full 2-level model. So what's the intercept in this case, right? Well, the intercept is, again, this expected math achievement when everything else in the model is 0. So when when sector group mean centered is 0, or sorry, SES group mean centered is 0, when sector is 0, which means for a public school, and when mean SES centered is 0, which means a public school of average SES, right? So this overall intercept is really like sort of the expected math achievement for a school of average mean SES, right? A public school of average mean SES. And because I group mean centered, SES, it really is for them, it is the mean within the school on SES. So you don't even really have to say that in this case. You could really just say that it is the predicted, right? This is the expected value for an average SES public school, right? I mean, again, if you want to say for a kid of average SES in their school, right? So a kid whose SES is at the average for their school, and it's the average, you know, the school is of average mean SES and it's a public school. Yeah. Oh, yeah, sure. Oh, the one that you need for which? Oh, textbook. Oh, yeah. So you may have to install that one. Although again, you should be fine for class right now because we just attached all the functions that were in there. So if you're getting that error, you should be fine. Okay. So then again, so that's this. The gamma not, or sorry, we just did gamma not. Gamma not 1 now is the effective sector on the randomly varying intercept, right? So, and gamma not 2 is the effective mean SES on the randomly varying intercepts, right? So what's the intercept? Well, the intercept, those randomly varying intercepts are really, again, you know, sort of we've got within school SES is 0, right? So it's sort of the effect of the effective mean SES, right? When, you know, when students are at the sort of the mean in their schools, right? And the effective sector, when, you know, again, when students are at the mean in their schools, but again, like that's sort of the overall expected. Yeah.
So not 1 is which number?
The gamma not 1 is the effect. So that's this one. Gamma not 1 is the effective sector.
Is 1.22.
1.22. So what does that really mean? Well, actually, maybe it's more helpful. How do we interpret this model? Here we go. I wrote it all out for you. All right. So in public schools of average SES, the expected math achievement is 12.13. That's my gamma not. In Catholic schools of average SES, that expected math achievement is 1.23 points higher, right? Which is that gamma not 1. And if I wanted to know what the expected math achievement is in Catholic schools, then I add 12.13 plus 1.23, and I get 13.36, right? And the achievement difference between public and Catholic schools is actually 1.23, favoring the Catholic schools. And it is statistically significant, okay? For every unit increase in school mean SES, the expected math achievement in the school goes up by 5.33 points. And again, remember I have this, I'm group mean centering SES right now. And technically, this is actually true in both Catholic and public schools because I did not include an interaction between mean SES and sector.
And so that's gamma naught.
So gamma naught 2 is saying that that for every unit increase in SES, right, in public schools, that the expected math achievement increases by 5.33 points. But it turns out that because I didn't put an interaction, I'm not actually allowing for the effective mean SES to be moderated by sector. So it turns out that that is actually true in both Catholic and public schools. And then in public schools of average SES, the school effective SES, the within school effective SES is 2.95. That's that SES underscore C coefficient, which means that in a public school, has to be a public school. So this is when sector is 0 and when mean SES is 0. So in a public school of average SES, a 1 point increase of SES, that predicts a 2.95 unit increase in math achievement. Okay?
That's gamma 1 up.
That's gamma 1.0. That is the intercept of the slope. So it's when everything in that model is 0, which is when sector is 0 and when mean SES is 0, for every within school increase of 1 unit on SES, I expect a 2.95 unit increase on math achievement. But SES and sector both moderate. I have cross-level interactions. They both moderate the within school effective SES on math achievement. So the within school SES slope is more positive in schools of higher SES, higher mean SES. How do I know that? Well, again, if you look at our summary, right, we've got 5.3329, right? So here we go. So in a public school that has high mean SES, where mean SES is 1 unit above the mean, the effective SES on math achievement is 2.95 plus 1.04. Where did I get the one? Oh, yes, there it is, the cross-level interaction. Good. Is 1.04, right? So that's the effect of mean SES on the SES slope. Does everybody see that 1.0393? So that's saying, so the 5.33, that's like the effect of mean SES on math achievement, sort of, right, when SES, like, 2 minutes. Oh yeah, I do have to go soon. When SES within school is at the mean, but now this 1.04 is the effect of mean SES on the effective SES on math achievement. So what I'm saying here is, in a public school that has high mean SES, the effective SES on math achievement is actually 2.95 plus 1.04. And in a public school of low mean SES, the predicted SES slope is actually going to be 2.95 minus 1.04. So in Catholic schools, the effective SES on math achievement, we also see now that sector on math achievement, that's that negative 1.64, right? In Catholic schools, the effective SES on math achievement is less positive, right? It's more negative. So in Catholic schools, the effective within school SES on math achievement is 2.94, right? Minus 1.64, because this is the effective sector on the effective SES on math achievement. So in a Catholic school of average SES, the effective SES on math achievement is predicted to be 1.3 points. In a high mean SES Catholic school, the predicted effect is going to be this. By the way, we're going to do more with these predicted values next week, I promise you. And in a low mean SES school, right, the predicted SES slope is actually really near 0. It's like 2.94 plus negative 1.64 minus 1.04, which is 0.26. And you might be asking yourself, well, is that 0.26 statistically significantly different from 0? And I don't know, because I computed that, but I don't actually have a statistical test for that. I have no standard error for it. So what would you do, by the way, if you wanted to test that for statistical significance? The easiest thing is to just re-dummy code your variables differently so that you actually get this as a parameter in your model. All right?
Does the negative 1.64 and the 1.04, do they have what letters are that?
Well, the negative 1.64 is let's see, gamma 1, there you go. And the other one is gamma 1, right? And again, you could call sector 1 and, somebody else might have sectors 2, that's fine. Or you just need to be consistent within your own model, right? Because, what you put in first is going to be gamma 1. Okay. Last but not least, okay, I'm not going to do the Kenwood Roger. But if I wanted to look at like, how well does this model compare? We're just going to do one model comparison. How well does this model compare to a model, let's say a model that doesn't have randomly varying intercepts and slopes, randomly varying slopes, let's say.
Not to let you run over and it's like 46.
Okay, just 1 minute. 1 minute and then I'm going.
I solved if you miss your flight.
I'm not gonna miss my flight, but you want to do this?
No, I'm just letting you know.
Okay. All right. So let's say, hold on, we're gonna skip down through all of this. I ran 3 models here, but I'm obviously not gonna have time to do both of them. So my 3 models are an unstructured tau matrix, right? Model 6A constrains the slopes and intercepts to be uncorrelated. So I have 1 fewer parameter than model 6, but I'm still allowing for a randomly varying slope. So 6A says I've got a randomly varying slope, I've got a randomly varying intercept, but I'm constraining the slope and the intercept to be uncorrelated with each other. And I can do that. How can I do that? Well, hey, I should show you this code actually. How can I do that? It's really easy. Notice I've got double bar. The double bar here is saying, so I've got SES underscore CWC double bar. That double bar is saying, yeah, estimate a randomly varying intercept and a randomly varying slope. Don't let them correlate with each other. And if I do that, okay, I can run that model. I can get my summary. I'm going to worry about the compare, but I do want to do this. Well, I can run the compare, I guess. Let's get to the ANOVA. Shouldn't have done compare. Hurry up, compare. Comparison, but now here's my ANOVA. This is what the ANOVA table looks like, and I just want to walk you through this really quickly, and then I'm going to run in my clock. Okay, so in model 6A, it's nice because it actually shows you what the model is, right? So model 6A, I've got math achievement is a function of blah, 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 right? And then it's got this, so I know I'm not allowing for the covariance, versus model 6 that shows you what that model is, and so I can see what's going on. Model 6A has 9 parameters. The parameter I'm not estimating is the covariance between the randomly varying slopes and the intercepts, right? These deviances are going to be, fine. They're going to be recomputed with Fimmel, but that's not a problem. And then I get the chi-square difference between these 2 models with 1 degree of freedom. And because here, this is a covariance, I don't even have to worry about the adjustment. The chi-square difference is 0.9. Likelihood ratio difference is 0.9. With 1 degree of freedom, a chi-square difference of 0.9 has a p-value of 0.34. So that means that getting rid of that covariance basically fits as well as the model where it had the covariance, right? So I would favor the simpler model. So like now that I've done this test, it probably would be reasonable to not estimate the unstructured model, right? Because as you can see, the deviance changes like really almost not at all when I do that. Okay, but one more. I have to do 6B. I just have to. I will be fine. Okay, and then 6B. In 6B, I get rid of the randomly varying slope altogether. Okay, so now this is going to be 1 degree of freedom fewer than 6A and 2 degrees of freedom fewer than 6. And I'm going to run my my ANOVA go? Oh, here it is. So now here I'm comparing, you could compare 6B to 6A, by the way. I'm not going to do that. I'll leave you to do that on your own. So I have it go. But 6B to 6, this is a 2 degree of freedom test because 6 had the variance and the covariance, right? 6B eliminates the randomly varying slope, so it also then eliminates the covariance between the slope and the intercept. Is everybody with me? And now I see that the difference in deviance between, it's now a 2 degree of freedom test instead of a 1 degree of freedom test. The chi-square difference is literally like 1. A chi-square of like, I compare that to the, again, like technically one of these is a variance and one of them is not, but it really doesn't matter because no matter how you slice it, this is definitely not statistically significant, right? My p-value is 0.6. There's only a change of like 1 with getting rid of 2 parameters. So I'm not even anywhere near statistical significance. So this would suggest it's not, the answer isn't really to get rid of the covariance between the slopes and the intercepts. The answer here is just get rid of that randomly varying slope. I don't need it, right? Now I could run another model, which I have on there, I think, where I get rid of the randomly varying intercept. And if you do that, you'll see that the chi-square goes up by well over 200 points. So I need that randomly varying intercept still, but I don't need the randomly varying slope. Okay, gotta go, I really do. So, can you shut everything down for me? All right, have a great week. Wish me luck getting to my flight.
See you
Yeah,
tonight or tomorrow in DC.
yeah, I hope so.
I hope so. I'll make it. The question is, will you? Oh, did she turn off the recording? I don't think so. I don't know. Yeah, yeah, but it's still. Yeah. There we go.